Very nicely done. You guys you can head out to Rob there. Thank you so much. So now let us make linked lists look much less exciting with actual code, just to get a sense of what happened here and how to start thinking about this. You'll find that we've implemented all of that now for you, and you'll find this will be particularly useful for problem set 6. One of the challenges in problem set 6, recall, from a much earlier teaser, is to implement the fastest spell checker possible. Now, at first glance, this might seem a little mundane, but it gets hard when the list of words, the list of English words you're going to be handed is like 150,000 words long, and you're going to need to somehow read those in from a file, much like you're doing already with problem set 5 this week. But then you're going to have to somehow lay out all 150,000 of those words in memory so that lookups, spell checking, is incredibly fast. Now, the simplest implementation of a dictionary is actually pretty simple, right? You allocate enough RAM, enough bytes to fit all 150,000 words, and you just load them up into a huge array, right? One word after another, much like argv contains all of the command line arguments. It's not hard to implement a spell checker or a dictionary if you just put everything in an array. But what would be the runtime? What would be the big O notation for spell checking a single word, if that's your implementation? Big O of... So if you have n words, or 150,000 words, let's genericize it as n. Big O of what is the running time of spell check in the implementation that uses an array? Right, it's n, right? It might be n over 2 on average, but we always get rid of constant factors. So big O of n is actually pretty fast compared to some of the horrible sorting algorithms we played with, right? Bubble sort, selection sort. Those things really underperformed compared to things like merge sort. But relatively speaking, even linear time is something that you might want to avoid. What's an example of a running time that we saw that was actually better than linear? And what algorithm did we see that in? Yeah, so binary search, right? This divide and conquer approach where we counted students or we found numbers behind pieces of paper on the board. So log n is even better. But now, the holy grail this week and next is going to completely one-up ourselves and try to achieve constant time, whereby even if you have 150,000 words, the challenge ultimately in problem set 6 is going to be to get as close as possible to instantaneous lookups. No n, no log n, nothing other than constant time. Now, we're almost going to be able to get there. But you'll see that it's going to require some ingenuity. Among them, tricks like linked lists and something called hash tables or tries and trees and the like. So more on that to come. But for now, let's take a step toward it. So here is list1.h. And here again is, just to be clear, the structure that each of these guys, except Lisa, represented a moment ago. Each of them had an int n held up on paper. Each of them had a left hand called next. And now those were our 8 bytes that each of these guys represented. Now I'm going to go ahead and open up list1.c. And we won't dwell on all of the minutiae here, because it can actually, frankly, unless you kind of work through it slowly, it's very easy to get lost. But let's take a look first at what this thing does. Let me go into a terminal window. Let me do make list1. And let me go ahead now and run list1. And you'll see that just so that this is interesting, I created sort of a poor man's menu here, whereby it just waits for you at this command prompt to either type in delete, find, insert, or traverse. All of those should be self-explanatory, except traverse just means start at the beginning of your list and just print out all of the numbers. That's all we mean there. So I just needed a little menu because I wanted to implement functions called delete, find, insert, and traverse. So what do I want to do here? Let me move this slightly over and do delete. Well, there's no number to delete, so the list is empty. So let's actually start with insert. I hit 3 for insert. What number do I want to insert? I'll insert the number 5, just like we started with there. So now, just to see what's going on, every time you execute a command, I wrote the program in such a way that it just tells you, it reminds you what the current list is from left to right, just like our humans. So let's do another one. Insert. I'm going to insert, let's do the exact same numbers. So I had 5 in there before. Let's also put in the number 17. That was among our numbers. Let me do another insert, this time for 9. So those are 3 of the numbers we had. And notice now that the program is, at the moment, smart enough to actually insert at the right location. 55 is going to go all the way at the end there. And I can continue this. And I could insert all of the same numbers that we had up here on stage. So now let's peel back the implementation and see how this is working. So first, what do I need at the top of this program? So I've got a bunch of includes. We haven't seen all of these before, but I'll wave my hands at the new one there, unistandard.h, and just point out that, one, I'm including my own file, and that has the type def we just saw. And I also have a global variable. I could avoid this, because remember, we've generally preached that global variables are bad. But when you're implementing a program, as in this case, whose sole purpose in life is to do one thing, implement a linked list, it's pretty reasonable in this scenario to have a global variable. Just like in the game of 15, we had a big global variable there called g, because the whole program was dedicated to the game. We might as well have one global rather than pass the same pointer around again and again. So here is essentially, I could, to be clever, just rename this Lisa, right? So Lisa represented this pointer here. So she's 4 bytes, which is implied by the fact that there's a star there. Even though a node is 8 bytes, remember that every pointer is 4 bytes. So this variable now represents Lisa. But I'll go back to the global variable here called first. And that was the piece of paper Lisa was holding up. So that's Lisa, and she's initialized to null. And this, too, is important. If you don't initialize Lisa, or the head of your linked list, to null, you're going to assume that whatever garbage value was in Lisa's left hand is an actual node. And if you follow that pointer, bad things are going to happen if no one existed to the left of Lisa. So this is incredibly important now to always initialize your pointers to some known value, for instance, null. Now, I've got some function prototypes, and I promised that those things would exist. Let's scroll down to main. So main, here's how I implemented the menu. As we've done in the past, I have a do-while loop, and that's how I keep prompting the user again and again. Here's just the menu. It's kind of formatted in this way for just aesthetic purposes. As an aside, if you've never known this, if you have a really long string that you want to print with printf, and you don't want it to wrap and wrap and wrap around, you can actually close the quotes, as I did here, and then just hit enter, and then put multiple quoted strings on each line with no other punctuation, no commas, anything, and they'll be automatically concatenated together. They'll be attached to one another automatically. It's just a trick for keeping your code a little prettier. So here's where I say command. I use a getInt call to get the command. Then I have a switch statement, and this is nice and clean, because if the user types in 1, I call delete, 2, find, and so forth. So all of that is kind of older constructs. And then I have this trick here. If the user types in 0, that's how they would quit. Now, this is not the most friendly interface. It'd be nice if I supported Q for quit and the like, but that's really not the goal of this program. Let's focus instead on the linked list. So notice here that at the very end of main, I already had the foresight to free this list. And so if you assume that the user might start inserting nodes, that means that you're going to call malloc a whole bunch of times. So in my main function, before I quit, I want to make sure to free any memory that's been allocated by this program. Now, how does this work? We'll come back to this. But here, I have a temporary pointer. That was me. I was this temporary variable in the story. I'm pointing at the same thing Lisa's pointing at. So this is actually important. Lisa, a moment ago, so Lisa took her paper, but suppose this was Lisa here that said first. So if I say pointer gets first, what am I pointing to? Here's first. OK. So here's Lisa. Here's me. What am I pointing to when we do this highlighted line of code? Pointer gets first. There's kind of 2 answers. Am I pointing to Lisa? Or am I pointing to whatever she's pointing at? So I'm actually pointing to whatever she's pointing at. Because consider what's going on here. What is first? Well, first is a pointer, and it's declared up here. Well, what does that represent? Even though we refer to this thing as Lisa, Lisa contains a value. Her left hand represented that value. So if I say pointer gets first, that means do exactly what Lisa's doing. Put inside of your 4 bytes exactly the address that Lisa was storing, and that happened to be the address of like number 5 or number 9, whoever was there at that point in time. So I'm going to actually be pointing at the exact same thing that Lisa is, but not at Lisa herself. So what then happens? Well, this is just a trick, and this is very common in linked lists and data structures where you need to free a bunch of stuff again and again. I have a while loop, and I'm saying while my pointer is not null. So while I'm pointing at a legitimate person, and you can see how this story ends, right? If I get to the end of the list and then I follow the pointer, eventually I, the temporary variable, will be pointing at the ground also, null. So that's when that loop will stop. And for now, this is what's going on when you needed to remember, before freeing something, how to keep track with fingers in code here. So I butchered that sentence. What I mean here is this. This line of code obviously frees a pointer. It frees a struct. So what are these 2 doing? Well, there's one new piece of syntax here. So when I am standing here and I am pointing at say, the first node in the list, number 5. I am then going to go ahead and create a duplicate here, pred pointer, which is also, whoops, I have it here. These two are temporarily equivalent. So I'm pointing, pointer is at this guy here, say number 5. Pred pointer at the moment is also pointing to number 5. But what does this line of code then do? This is the only new one. Pointer, who's currently pointing at 5, gets pointer arrow next. So that's saying go to this guy, follow his left hand, and point at whoever was to his left, which in this case I think was the number 9. So in short, this piece of code here, and it's nice that the syntax actually uses an arrow, says update pointer to be equal to whatever it's already pointing at, which is pointer, but follow that next field, follow the arrow. So this one line of code is just my way of, again, having a temporary variable pointing at this person. And if I want to point at the next one, I need to follow that arrow to 9, follow that arrow again and again and again. And if I keep doing that, remember that 55's left hand was pointing down. So as soon as I follow that arrow, my own PTR variable is also going to be null. Now, why did I keep pred pointer around? Well, you could do this in different ways, but I needed to make sure that just because I advance to the next pointer, I need to make sure that I don't orphan the previous person. I need to remember them because I need to advance this pointer and then delete, or rather free, this person. Suppose I did the order of operations differently. Suppose I did this, free pointer, which feels very reasonable, and then do pointer gets pointer next. I mean, frankly, this is kind of intuitively, I think, much more straightforward. Free what you're pointing at, and then update yourself to the next pointer, and then repeat. But why is this bad? Because I already, exactly. As soon as you call free on a pointer and thus a struct, you are not allowed to touch that memory anymore. Because it's possible the OS, even though it's just between 2 lines of code, it's possible the operating system might need that chunk of memory immediately allocated to someone else. And voila, you've just now followed a pointer that's no longer your own. In reality, that's not quite how the story is going to go. But the idea is the same. Once you have freed memory, it is no longer yours to touch. It could, in fact, be reclaimed and used in some other form. So that's why, frankly, we have to kind of jump through these hoops and, frankly, make the code more complex and harder to understand. But all we're doing really is implementing these idea of temporary fingers pointing at these nodes and only freeing them once we get the ordering right. But for now, let me wave my hand at that. And let's focus on, say, insert. So insert is actually a little long, but we'll look at just a couple cases. Right? And so this is where pointers get interesting. But realize we're providing this code for a reason, so you don't need to implement it all from scratch. So how do you go about inserting a number, like the number 5 or 9 or 55 or whatever, into the list? So first, I need a node. So I'm going to call malloc, and I need as much RAM as is the size of a node. And then I store that address of memory in new pointer. And then I just do a sanity check. If new pointer is null, I'm just going to return, because I'm obviously out of memory. Something went wrong. Can't proceed. So that's what creates an empty human on stage with no number and no pointer just yet. All right, now I initialize the node. Number to insert. Well, I'm just using getInt. And here's how, given a new pointer, so given a human on stage, here's how I update his or her n field, the integer. And then I initialize the next field to null. So let me just point out one thing syntactically. This is kind of new, this arrow notation. And remember before when we've used structs, we use the dot notation. Why am I not using the dot notation here for new pointer? Even though I claim new pointer is, at the moment, because I've called malloc, this is what our picture looks like. This is our node. This is n. This is next. This is new pointer. And if we could try our camera trick. So, whoops, didn't see that. So this is what just happened. When I call malloc, I get this. When I store the return value of malloc in new pointer, I get this picture. And so this is